Welcome everyone. In today's presentation, we are going to show a case study illustrating the application of a full waveform inversion algorithm to image a steam chamber in a thermal bitumen project. First, we'll start with a general discussion of FWI. Then we'll review the results from a case study, and then finally discuss applications and challenges. The input data to the FWI algorithm are the shot records with an objective of deriving a velocity model that would produce matching simulated shot records. On steam-assisted gravity drainage projects, steam is injected into the reservoir to produce bitumen. The replacement of bitumen with a gas phase produces a significant seismic velocity anomaly. The output of the FWI process is a velocity depth model, which can be directly used for steam chamber interpretation. Another objective is to reduce the turnaround time to receive results that would allow more timely production decisions. We first tested the FWI process on a synthetic 2D data set using appropriate rock and steam chamber velocities. This included a blind test where we embedded various steam chamber geometries in a data set sent to the processor without providing any information. The test was very successful, which led to applying FWI on a 4D field program. This animation illustrates that the entire wave field is used in the model. You can see as the wave field progresses downward, it's impacted by the presence of interfaces, and also there is distortion due to the presence of the steam chambers. The FWI workflow is relatively straightforward, where we input the raw field data and match it with the simulated data using the FWI algorithm to produce a velocity depth earth model. This iterative process is very computationally expensive because the earth model must be built up with iterations of forward modeling and gradient calculations. We're now going to show results from a SAGD project in northeastern Alberta in the Athabasca oil sands area. The average reservoir properties of the Sunrise project are shown here. The Sunrise 4D was a challenging data set for the FWI project. We had different types of receivers, different receiver depths, different sources such as dynamite and mini-bibe, and also different source depths. This required a lot of QC work up front by the processor GeoTomo. Also, we did not provide any initial constraints to the FWI processing, such as a starting velocity model or by fixing certain layers. We've listed here some of the pre-processing steps that were used and also some of the strategies employed while processing the FWI volumes. For the baseline 3D, we used the standard FWI workflow to invert the baseline velocity model, which consisted of geometry validation, amplitude balancing, first break picking, and travel time tomo to develop the initial model for the FWI and then finally deriving the baseline velocity model. For the monitor 4D, we used a double difference approach to invert the difference between the baseline and monitor and then add the difference back to the baseline final model to get the final monitor velocity for PSDM processing. The difference model can be directly used for the steam chamber interpretation. This is an example showing how the FWI algorithm converges until the field shot gathers, shown in black, match the simulated shot gathers, which are shown in red. We'll show examples of the control data we use to QC the velocity model results. Here we see in the lower panel a typical pre-stack time migration cross-section with interpreted top and base steam chamber surfaces picked. Then these time surfaces were converted to depth and overlain on the FWI velocity difference model result for comparison. In this case, there is a good agreement in depth and geometry, which provides confidence in the FWI results. The upper panel shows the PSTM volume used to pick the top base steam chamber events independent of the FWI results. The lower panel shows the improvement in imaging after applying the FWI velocity model to produce a PSDM volume. In this east-west cross-section, we show how the temperature logs in the vertical observation wells provide another set of control data. The horizontal well sticks are shown here projected onto the cross-section. The velocity difference color legend was adjusted to correspond with steam temperature in the observation wells. In this example, we show good agreement where the observation well indicates no heating is occurring in the reservoir. You can also see the horizontal well pairs projected onto the cross section and that there's good agreement between the injector, which is the upper well stick, and the interpreted FWI steam chamber. Identifying where no steam is present has important value in placing future infill wells. Here we are comparing a horizon slice from the FWI velocity volume against the time delay observed on a horizon below the steam chambers. On the left is the horizon slice of velocity difference at an approximate elevation 16 meters above the producer wells. And the time delay map is on the right-hand side. Note that steam variations along the horizontal wells can be observed on the inverted FWI velocity difference and not on the time delay map. This illustrates the improvements in resolution. Here's an example of the kinds of data integration that can be carried out using the FWI data, observation well temperature logs, producer gamma ray logs, and several types of well interventions. The two types of well interventions shown here are tailpipes, which redirect the emulsion flow, and GDAs, which are steam injection locations. Analyzing these data with the reservoir and production engineering teams can provide insights for further production improvements. Now we're going to see a 3D perspective video that illustrates the detail in steam chamber geometry from the FWI velocity difference model. The results were matched against the control data and then incorporated into a number of recommendations for infill well placement and well interventions to improve production. We're going to look at the steam chamber geometry from a number of orientations. And then finally, we're going to look at cross-section slices to see the detail along the well bores. Now we're going to review the applications and challenges that we faced. It's just as important to know where the steam chamber is absent to identify undrained portions of the reservoir. We also attempted to quantify the undrained areas for the reservoir engineers so that we could rank the importance of future infill wells. Ultimately, the goal is to improve our reservoir description and increase production. We will also use the information to better our understanding of the barriers and baffles within the reservoir interval. This was our first attempt to apply FWI technology to image steam chambers on a SAGD project. The depth model is not a true depth, so it may need corrections applied. In this project, we had a well-determined surface just above the reservoir that we could apply a depth correction to the PSDM volume and then to the velocity difference volume. We observed areas with poorer agreement between the depths obtained from the FWI solution and surfaces derived from the time volume. It's also possible to have non-unique solutions, but we have not investigated that risk in any detail yet. Finally, we note that this was a challenging data set given the significant variability in acquisition parameters. We intend to continue evaluating the use of FWI on future programs given the exciting results we obtained on this project. Thank you for listening, and do you have any questions?